And we have a great lineup of speakers throughout the semester, and of course, we'll continue through this year. With that, it's my great pleasure to welcome our first speaker of the semester, inaugural speaker of the semester, Stephen Moore, and from Aptiv. And the formal introduction will be done by Debanjali, who starts the chapter president. With that, over to Debanjali for the formal introduction. Thank you, Stephen, and thank you, everyone.
Thank you, Professor Mukherjee. So I will just give a brief introduction of our chapter and welcome today's speaker. So I'll just share my screen. Is my screen visible?
Yeah.
Okay, perfect. So hello, everyone. For those who are new, a warm welcome to the Electrochemical Society student chapter at Purdue. And for those who have been following us so far, welcome back. I'm Debanjali Chatterjee, a second-year PhD student at the Energy and Transport Sciences Lab and chapter president. Founded in May 2019, the goal of this chapter is to promote discussion and collaboration between students and researchers working in the field of electrochemistry for energy storage and conversion. I would first like to introduce our chapter advisory board. We are led by Professor Partha Mukherjee from the School of Mechanical Engineering at Purdue, who is our lead faculty advisor. Dr. Judy Jevarajan, Corporate Fellow and Vice President of Research at Underwriters Labs, is our distinguished industry advisor. We also have Professor Rebecca Chase from the School of Mechanical Engineering and Professor Julia Laskin from the Department of Chemistry at Purdue as our co-faculty advisors. Let me present a quick overview of our chapter activities over the past year. In spring 2021, we conducted our signature webinar series on women in electrochemical sciences and engineering. Comprising of a stellar lineup of women researchers from industry, national labs, and academia, both in the US and abroad, this series was exceptionally well received and appreciated in the scientific community. Inspired by its success, in fall 2021, we launched a webinar series on one of the hot topics in energy storage research, solid-state batteries and electrochemistry, inviting some of the leading academic and industry experts in this area. We are proud to announce that for our efforts in actively promoting scientific engagement and outreach on a global scale, we were awarded the 2021 Chapter of Excellence by the Electrochemical Society. The theme of this year's webinar series is Modeling, Characterization, and Analytics in Electrochemical Energy Systems, abbreviated as MoChA. Our first speaker is Stephen Moore, Director of Battery Management Systems at Aptiv. A graduate of Texas A&M University with degrees in electrical engineering, power electronics, and control theory, Stephen built his first electric vehicle in 1992 and has since continued to be involved with hybrid and electric vehicles, working on the BMW fuel cell vehicle, Renault drive-by-wire system, Shanghai Automotive Industries hybrid sedan, Fiasa Uno 48-volt hybrid, Hyundai T-hybrid, Bosch glider system, and the Allison transmission Class 8 hybrid system. His specialty is optimizing battery chemistry with vehicle integration using model-based controls. At Aptiv, he is responsible for developing the next generation of model-based battery controls for vehicle electrification. Stephen is the author of several patents relating to battery technology and control theory. He was the founding chairman of the International Electrotechnique Commission (IEC) regulatory and standardization body for large capacity secondary lithium cells and batteries, and was the founding chairman of the NEMA Grid Interconnected Energy Storage Council. He also served as a United Nations arbitrator for international regulatory disputes regarding lithium-ion battery manufacturing, safety, and commerce. Stephen, we look forward to your talk.
Thank you very much for the introduction. Yes, I'll get my screen set up. There we go. Everything should be working properly.
Yes, perfect.
Yeah, so thank you very much to the Purdue chapter of ECS. Sorry about that. Yeah, audio working now?
Yes, yes.
Great. Well, thank you very much, everyone, and thank you especially to the ECS chapter of Purdue University. I've had a long relationship with the ECS and always enjoy going to the ECS symposia. So thank you very much to the chapter, and thank you very much, Professor Mukherjee, for hosting as well. I very much appreciate the opportunity to talk today. So the name of my talk is Modeling the Lithium-Ion Battery Cells, Empirical and Physics-Based Approaches. And as you'll see in my agenda, I've kind of tweaked my topic a little bit. So we're going to have a little bit of fun here, moving a little bit more into a tutorial today as far as the approach. So just a little bit of history about myself. I got a couple illustrations here. I built my first, as the introduction says, I built my first vehicle in 1992. It was actually a zinc bromine flow battery. The picture up there in the corner was actually taken in Mesa, Arizona for the APS 500, which is a very early electric vehicle racing circuit. After that, I spent a long time working with solar car vehicles with the GM Sun Race, which then became, let's see, was the Sun Race and then the Solar Challenge as well with Texas A&M University, and a couple other vehicles there, the T-Hybrid out of Rüsselsheim, Germany from Hyundai. There's a picture of me with a Segway, which is a very interesting project because the Segway is a inverted pendulum, and model-based controls are extremely important in the Segway scooter, especially as related to the amount of motor torque that the motors exert on the scooter to keep the rider balanced. And so within that scooter, I wrote the impedance estimator in the battery. So that way the battery would be able to report its impedance to the motor controller, and the motor controller that could then estimate what the motor current would be, and therefore would be able to predict what the motor torque was going to be to keep the inverted pendulum upright. So a couple interesting projects there in the introduction also as well. I was part of IEC ISO for a long time as the chairman for large format lithium ion batteries, which now is being more and more used in the vehicle space. My current job right now is I'm the director of battery management systems at Aptiv. Aptiv is a Fortune 500 company. It's a tier 1 automotive supplier. Aptiv is being very aggressive get into the electric vehicle architecture. You can see the photo there is what we call the skateboard. It's a battery pack system with bus bars, integrated power electronics, and some other features in it. And so we're developing the next generation of model-based controls for the battery pack system. And the effort is a new effort within Aptiv for the BMS, and so I am currently hiring, and I'll say a couple words at the end of this presentation to that. So if you're one of the audience members who can pick out where I went wrong in my differential equations as I go through my presentation, you are more than welcome to talk to me at the end of the presentation because I do have job positions open. So the agenda of today's presentation is I just give a quick little introduction to empirical modeling, but then I'm going to actually spend the majority of my presentation on a tutorial on complex impedance and Nyquist plots. As I was developing today's presentation, it really dawned on me that I was talking kind of a whole lot in the Nyquist space. So I thought, well, maybe today's presentation I can spend a couple minutes really talking about complex impedance and Nyquist plots and how they apply to batteries, and really get a solid introduction to empirical modeling based on that. Then I'll move forward to a couple of the more sophisticated techniques, Warburg impedance and constant phase elements, and then show what the limitations of these empirical modeling elements propose, and then move a little bit into an introduction into the physics-based modeling and show how those can conquer some of those limitations. There we go. Just give an introduction to lithium-ion batteries. I really am not sure of exactly who's in my audience today. I figure since this is an ECS symposium, you've been exposed to a great deal of these things, maybe not particularly for batteries, but been exposed to a lot of the different technologies that batteries would involve. But a lithium-ion battery basically consists of an anode and a cathode that's pictured over on the cartoon on the left-hand side, where there's some sort of lithium metal oxide. It could be a cobalt oxide, manganese oxide, nickel, for instance, or it could be even an iron phosphate, which is olivine. So the cathode could be a variety of different lithium substances, and then there's a separator, and then on the other side is the anode, which is typically some sort of carbon matrix that the lithium ions intercalate into. So during this presentation, I'm going to be talking about cells. A cell is a single set of these anode cathodes. So it represents only one electrochemical voltage potential. And then you have battery packs, which would be more than one cell wired together. And I got a little example of a cordless drill. The cordless drill battery, they're battery packs. They contain more than one cell, and we're not going to be talking about those today. We'll just be talking about individual battery cells. So in the modeling continuum, I've got a little graph here that shows model complexity, as in the number of parameterizations, perhaps CPU complexity, the complexity of the mathematics involved in those models, etc., versus the predictability, meaning how well can the model predict what's actually happening inside the cell. And so the bottom corner is an equivalent circuit, and is named after Randall's. The Randall's model is the equivalent circuit model, which we're going to get into today. And then once you get up out of the empirical models, you get into some physics-based model, which actually tries to replicate some of the physics going on inside the cell. So one of the ones would be a single particle model, which we'll show here in this presentation as well, and a porous electrode model, which now you have lots of particles and lots of things going on and lots of things to model. Of course, the complexity gets very, very high, but then the predictability also gets very high. So we're going to start with the Randall's model. And I don't really have very much audience feedback here, so I'm just going to plow through this. I do really enjoy being in a classroom setting where I'm able to interact directly with the audience. So I'm just going to plow through this here because the online is a little bit of a different forum for me. So looking at a single cell, the easiest possible model for a single cell is just simply a voltage source. And most lithium-ion cells, the one in your cell phone, the one in your watch, your iWatch, or whatever you have, or these 18650 cells that I have shown in the picture, these are usually cobalt-based cathodes, and they run about 3.65 average. And so there's lithium cobalt oxide, lithium nickel manganese cobalt, other combinations. And then there's a lithium iron phosphate cathode material, which runs about 3.30 volts. And so this is really the easiest model. It's just simply the battery is a voltage source that puts out some voltage, and you can use it to power your load. And this is a model that you can use in some situations. And there it is right there. It just, over time, it puts out a voltage, and you can put a load across it and use the voltage. But in real life, these voltage curves aren't really a flat line. They move with how much lithium is in the cathode and in the graphite. Basically, as the lithium moves from the cathode to the anode, the battery discharges and the battery goes down in voltage proportionally to the amount of lithium that's being moved in the battery. And you can see all the different types of cobalt. There's lithium cobalt, lithium nickel manganese cobalt, lithium nickel cobalt aluminum, and they all have very individual curves. So it's not so simple just to use a voltage model. And then lithium iron phosphate has a flatter curve that averages somewhere around 3.3 volts. But if you zoom into that flat curve, you'll see that's the lower image where it's zoomed in. You'll see that the voltage goes up to about 3.3, then it goes up, and then there's another inflection point at 3.32, then it goes up again, and then there's another inflection point at 3.34, which this is all happening in the millivolt space, but it still makes the voltage rather difficult to follow. And not only that, iron phosphate continues, well, let's see. So we could use things like an exponential model, polynomial fitting. We could use sum of sines, Gaussian model. And at Purdue, there's a course, ME 584, which is a system identification course, which goes through a couple of these different techniques, and you can learn the different system identification equations that you could use to model this voltage with. Now, this would be using an empirical model, meaning you're modeling what is measurable. So you measure the terminals of the battery, you characterize the voltage, you employ your system identification techniques, and then you can write an equation that defines this voltage. The other way of doing it is actually getting in and looking at some of the physical mechanisms going on, the actual chemical mechanisms. And I have written here is the Nernst equation. So if you're not familiar with it, just enter it into Wikipedia, and you'll find out that the Nernst equation tells you electrochemical voltage potentials between materials that you could use to characterize for your cell. And I'm not going to get into this very much, but I just wanted to show you an example of the difference between using an empirical method and a physical method. So iron phosphate in particular is a really difficult voltage curve to characterize. And so this image right here shows an iron phosphate brand new, that would be the blue line, all the way to an aged cell that has been used 540 cycles on that cell. And you can see that these little inflection points that we looked at earlier, these inflection points down low on the curve, they all stay at the same, but the upper end changes. So if you tried to curve fit this, it would be really difficult because some of the inflection points don't change with age and other inflection points do change with age. And so this cell gets really tricky to model using empirical techniques because we can measure this and we can curve fit it and we say, okay, we've got this voltage curve fitted and therefore we know what the behavior of the cell is going to be. But as the cell ages, the inflection points of your curve fit don't necessarily age the same. And so at this point, we're going to have to either use a piecewise curve fit, or we'll have to use some physics-based approach to figure out what these voltages actually are and model them in real time. So moving on, we're going to take this equivalent circuit that we've developed a voltage for, and we're going to add a resistor into it, which is a series resistance, because we don't always have an ideal voltage source. And even if the voltage source has some curves to it, is still not ideal. There's always some sort of resistance there. And as current goes through this resistor, I get a voltage drop. And so I can look at an iron phosphate cell, for example, at different discharge currents. And as I have higher current, I get voltage drop across my series resistance, and my voltage sags. So higher current, higher voltage drop, the more my battery sags. And so this is a very linear approach, and there's a couple different ways I can find this R sub S. I can apply some test currents to the battery, and I can measure the voltage sag, and I can characterize what this voltage may be. So we'll look at a few of those examples here. In this example, I apply a current of maybe minus 200 milliamps, and then I perform a step at minus 2 amps, which is order of magnitude. And then I measure the voltages at these points. And then I apply a positive 200 milliamps and apply a positive 2 amps. And I measure the voltages at those points. And then I can plot my voltage versus current. So here's my minus 2 amp plot, my minus 200 amp, my plus 200 and my plus 2. And then I can draw a line through it and I can find the slope of this line. And the slope of this line is Ohm's law, which is a function of voltage and current. And then I can draw out the R sub S of this cell by observing the voltage drop at different currents and then drawing a line and finding the slope. And I can pretty well characterize this R sub S. Now, I'll have to perform this at different temperatures, because the R sub S changes with temperature. When a battery's cold, it sags more. So that means the resistance is higher. When the battery is warm, the resistance is lower, etc. And I'll also have to do it at different states of charge, meaning a fully charged battery will have a slightly different internal resistance than a discharged battery. So I'll have to try it at different states of charge and at different temperatures. And then I can create a pretty good model of what this R sub S looks like using this kind of technique. But now then I have to worry about complex impedance. And complex impedance, I suppose I have a mixture of both electrical engineers and mechanical engineers in the audience. And so all my electrical engineer buddies should be able to look at this diagram over here and say, okay, well, I know what a RLC tank circuit is. And I'm familiar with the reactive impedances of these elements. And the mechanical engineer friends in the room should all look at it and say, okay, well, I know what a dash pot is. And I am very familiar with the elastic strain and the viscoelastic strain and understand what the reactive impedance of a dash pot is. And so both of these are applicable, where an inductance creates a positive imaginary impedance or reactive impedance, and a capacitor results in a negative reactive impedance. And because of this, when I apply a waveform to the battery, meaning if I apply a voltage or a current to the battery, the other one will either lead or lag, depending on if it's reactive positive or reactive negative, or if it's being inductive or capacitance, I'll get a leading or lagging waveform. So this is my complex impedance. And a battery is not going to act as a nice linear resistor. It's going to act like a capacitor. And so this right here is a much more, this RC network is a much more realistic representation of my battery as far as what I see from the terminals. So if I have my voltage source, and my voltage source is supplying something to this little RC network, and I've got to pretend here that I've got a 100 ohm resistor and a 100 millifarad capacitor. Form. By the way, can you see my mouse on the screen? Can someone tell me if they see my mouse?
Yes, yes, we can.
Okay, great, thank you. So if I apply an AC waveform to this, the AC passes through the capacitor, so it's going to see 0 ohms of resistance. And so right here, this is called a Nyquist plot, which I'm going to spend a couple slides on talking about Nyquist plots, because this is where all the modeling happens. We're all going to look at the modeling today on the Nyquist domain. So at a very high frequency, all the signal passes through the capacitor, and my impedance is 0 ohms. However, if I apply a DC, which is an infinitely low frequency, it's all going to go through the 100 ohm resistor, and I'm going to be over here, my frequency is infinitely low. I'm going to be at 100 ohms. And in between infinitely high frequency and DC frequency, I'm going to have reactive impedance on the imaginary axes. Now, I'm graphing this imaginary axis minus because capacitors have negative reactive impedance. And so this right here is my Nyquist plot. It shows me. And right here, smack in the middle, where it's seeing 50 ohms impedance for at that frequency, that's called the RC time constant. It's right in the middle of the semicircle. So now I have a model that I can now put together, that my battery consists of a voltage, which we looked at the open circuit voltage graphs earlier in the presentation. Let's see, let's go back. So we have some sort of voltage coming out of the electrochemical system of my battery. And we feed that through an RC network, and I get this neat little diagram. However, we still need to take into account the series resistance that we showed earlier. And so by the time I add the series resistance, if I give a 20 ohm example here, and then an RC network with 100 ohms right here. So on the Nyquist plot, everything just moves over 20 ohms due to the series resistance. And then I have my semicircle of reactive impedance, and then I intersect the real axes again at 20 plus 100 ohms, real ohms right there. And so this now is beginning to get a lot better shape as far as being able to model what my battery is doing. And I can write this in differential equation form. In the canonical form, I can write a dV/dt, where my change of voltage over this RC network is some sort of function of the current that I'm applying to it, what is the voltage across it, and then of course the RC network itself. And then I can also solve and put this in discrete space, where I can do time samples. So if I have time sample K, and I want to go to time sample k plus 1, I can discretize this equation and then solve for time samples. And there's a couple of courses. I think there's Math 527 and Math 528. These are going to be some differential equation classes at Purdue. I believe that you learn about the Laplace transform and the Z transform, which are necessary transforms to convert from the canonical form of a differential equation to a discrete space equation. And for those who are not enrolled at Purdue and have the access to the classes that teach you this stuff at Purdue, there is a Dr. Plett over at University of Colorado, Colorado Springs, has a really nice lecture online about how to do this conversion right here from canonical form differential equation to a discrete space. So you can get online, and he has this lecture free online to do that. So there's a lot of different ways to do it. So I would expect in this audience, I'd have a lot of people who are taking these classes as it is. So I am going to show this differential equation in a bit more detail because it's very important, because if I look at the terminal voltage of the battery, V battery, and I'm going to solve for V battery, is going to be my open circuit voltage curve that we covered in one of the earlier slides, minus whatever voltage drop I'm having across my series resistance. So here's my series resistance right here with the current going across it, minus whatever voltage drop I'm incurring due to my RC network, which is the RC network right here. And my RC network in canonical form differential equation, I use the dot format right here, which is actually dV dt, which is just the dot form notation. So I can solve for this voltage, and I can figure out what my terminal voltage of my battery is. Now, in equation space, I usually work in the discrete domain, meaning I'm doing time step. And so I'm doing time step 1, time step 2, etc. So I can convert this V dot RC into a time step of the voltage across the RC network. And I can take my V battery and I can solve it and find it in time space right here with the subscript of the K as far as what this is. So what this equation shows is what is my present RC value, what is the voltage across my RC based on what was my voltage across the RC last time step, plus any new change due to the current coming through the battery. So now I have a reasonable empirical model that I can say I can reasonably model my battery's performance. I know what its voltage is. I know what its linear, my series resistance. I know what its linear voltage drop is. I know what its time domain voltage drop is. And so I have a reasonable way of predicting what my battery's performance is at this point. However, there's always another level of difficulty whenever there's modeling. So the next level of difficulty is the Warburg impedance. And if you're not familiar with this term, this is something that you can Wikipedia and you can find out what Warburg impedance is, or you can simply look over here. For those people who are familiar working in the complex frequency space, a Warburg is simply a constant phase element. And it's a constant phase element with its coefficient equal to 0.5. Or in other words, it's a 45-degree angle on the Nyquist plot. But in the physical domain, it actually means something. So if I look at this little cartoon of what a lithium-ion battery looks like, and I have these little dots over here that's supposed to represent my lithium metal oxide, and then I take a look at what that lithium metal oxide looks like, it's actually physical particles. So you can actually see it under a scanning electron microscope. It's actually got a lot of particles in there. And the lithium ions physically have to move through these particles to find a place to reside. And so you see these little red lines, that's the lithium ion, is going into these particles, is finding somewhere to live. And that is a time-dependent process of diffusion. And so the Warburg impedance tries to model this time-dependent process. Now, this time-dependent process is really interesting because the more lithium ions I try to cram into this current, into the electrode, it gets proportionally more difficult to cram the next one in. And therefore, when graphed on a Nyquist plot, it has this tail that goes off to infinity, there, infinity time right there. And so given my model here, and I have a 20 ohm resistor and a 100 ohm resistor, now I add a Warburg impedance on, and here's my semicircle. But once I hit this, the bottom of the semicircle, the Warburg impedance takes over. And the longer I continue to apply lithium ions from, and this lip right here, the RC time constant of this is usually the semicircle ends after about 1 second, which means this capacitor right here charges in about 1 second. For 18650 lithium ion batteries, this is a reasonably good rule of thumb that this capacitor fills in about 1 second, and then the Warburg impedance takes over after 1 second. So if I apply a 1 second pulse, I'll generally see this reactive impedance, but then I start applying 10 seconds of pulse or 100 seconds of current or 1,000 seconds of currents. My impedance of my battery continues to grow over time as those lithium ions are having to engage in the diffusion process in the electrode. And so this is the reason why your battery voltage sags as you're using your battery. If you're doing something like powering an electric motor, or if any of you have been in a robotics program and you built robots or electric vehicles, electric bicycles, any of the above, especially maybe if you're familiar with riding an electric bicycle, if you use the electric motor on your electric bicycle for maybe 1 or 2 minutes, you'll notice that your power is sagging. This is the reason why your power is sagging right here, is the Warburg impedance. Now, the Warburg impedance is a very real life mechanism. So right here is an actual Samsung 18650 cell with a nice real life Nyquist plot. And these have wound construction, and I really haven't talked about battery inductance very much, so I'll only say 1 sentence on inductance. These are wound constructions, so they do have some inductance, and it happens in this high frequency region, in the kilohertz region or so. You'll see a little bit of inductance, but then the capacitance takes over, and with the Samsung at 630 hertz, meaning any pulse you apply to the cell that's slower than 630 hertz, which is about 0.002 seconds, it's going to act capacitively. It's going to have capacitive reactive impedance. And then after about 1 second, it's going to start going up the Warburg tail, 10 seconds. And you see up here at 5 millihertz, which is 200 seconds, is way up here on the Warburg tail. And so this right here is the actual real life impedance of the Samsung cell. So you can see that this Nyquist plot is really, really similar to the one I can model. So this is a really good model, actually, for modeling terminal voltage. It's pretty close. It's close to me. I think it works. And it does work in real life. The problem is a Warburg impedance is impossible to convert into discrete time space. So if you're doing anything that requires data sampling, you can't do calculations for the Warburg impedance. It doesn't work because the differential equation cannot be converted using a Z-transform into discrete time space. So that gives a little bit of a problem of how to model this Warburg tail. So that's where it gets complicated. You have to do something like this. And I will explain this quickly, that you use a series of RC networks, and you maybe use RC network 1, and you draw the little semicircle, which approximates the Warburg impedance. Then you use RC2, and you draw another semicircle, which approximates the Warburg impedance. Then you do RC network 3, and you draw another semicircle, which approximates the Warburg impedance. And you just keep on drawing these circles, and you see that the green line mostly approximates the red line. And you can crawl up the Warburg impedance by just keeping on adding these things on. And my differential equation gets really nasty now, because now I have 3 differential equations, and I have 3 sets of parameterizations, and I have 3 sets of data I have to keep track of when I put it in a state space system. Now I have my original RC network, and I have 3 more differential equations. Now I'm dealing with a 4-dimensional state space system. So things get messy very, very rapidly. And I'm going to show you my next picture that this is where you would throw down your textbook and just walk out of your professor's classroom if he did this to you. So I'm going to do it to you right now. I'm going to show you a diagram like this. So this is a diagram of some lithium-ion degradation mechanisms. And over here is the anode, which is the negative electrode. And on the right-hand side, I have the cathode, which is the positive electrode. And there's all sorts of things that can go wrong in a lithium-ion battery. And I could talk, easily give you many hours of lecture over each one of these little topics. But some of the things are pretty easy to spot. Lithium plating, when you get around 0.1 volts at the anode, you can have some bad things happen with lithium. On the positive electrode, I have circled right here, you can get some bad things happening at your cathode, some electrolyte decomposition and some other things. And so when you really want an insight of saying, what am I actually doing to my lithium-ion battery? Am I doing something bad to it? Am I treating it the best that I can? Am I getting the best performance possible out of my lithium-ion battery? Am I optimizing the usage of my lithium-ion battery? These questions are answered on this kind of detail. And these are very, very physical representations of what's going on. So if I take a look at my Nyquist plot, and I see it right here, it's like, okay, this is a decent model. I can model what my battery's doing. But what does this actually mean? What does this mean to my electrolyte and my cathode and my anode? What does it mean to my degradation materials? What does it mean? But in the end, this model that we just spent the past couple minutes developing, it has absolutely no usable physical representations. So I just banged my head on empirical modeling. I can model the performance and I can tell you what my voltage is going to do, and I can tell you if my battery is going to sag if I do an acceleration on my electric bicycle more than 20 seconds. I can tell you those things. So I can tell you a lot of performance details about my battery, but I cannot tell you any physical representations of what's going on inside of the lithium cell and whether or not if I'm actually optimizing the utilization of the chemistries. So I'm going to have to depart from this in order to get more useful and educated insight on my battery. So one of the ways of doing it is just building a really, really complex empirical model. And I can draw a series resistance for my copper foil, and I can do a Warburg impedance and a constant phase element and a resistance for the anode, and I can do this for different components, electrolyte and separator and thin films and cathodes and aluminum foil, and I get this really massive circuit on the bottom, which is nearly impossible to simulate in time space because it has all these Warburg impedances and constant phase elements in it, which we just discussed we can't convert into discrete space. So this is extremely hard to parameterize, and it's also extremely hard to model. It's not really a good solution. So using an empirical model to try to figure out something like electrolyte decomposition, it's like, okay, well, I could try to build this empirical model, but it's not going to be very simulatable, and it's going to be extremely difficult to parameterize. Maybe it's not the best solution. So how do I find out what's going on with my electrolyte decomposition at the cathode? Well, I'm going to have to change to a physics-based model to get there. And a physics-based model is actually, instead of modeling what's happening at the terminal of the battery, a physics-based model uses the fundamental governing laws in nature to figure out what the battery's doing. So in this illustration, I have the negative electrode, which is consisting of a multiplicity of particles. And then I have a separator, then I have a positive electrode that has a multiplicity of particles. And I can try to model this, and this would be a porous electrode model. It would be very difficult to, there's a lot of parameterization going on and things like that. But I can take a look at sort of this group of particles, and I can say, well, what about this one group of particles? Well, forget that. What about one particle? Can I abstract a single particle and then try to figure out what is the diffusion of that lithium ion out of a single abstracted particle? And I say, okay, well, I can do that now. That makes a lot more sense. So I can move over here and create what's called a single particle model. And a single particle model attempts to model the physics of what if your lithium ion was literally one big cathode particle and one big anode particle, and I'm just modeling a lithium ion going in between the two particles. Now I can really get in and look at some of the fundamental governing laws of nature, and where I can make some conclusions about how this is going to work. And so this right here is a big messy slide, which we'll only spend about a minute on. But there's some dominant equations here, and this right here is a whole lecture on its own. But I just wanted to give you a flavor of what a physics-based equation looks like, because you're actually using some of the phenomena in trying to model it directly in order to reach your conclusion of what's going on inside of your lithium battery. And so the Butler-Volmer equation and Fick's law of diffusion are two of the dominant equations. There's a lot of other equations that are going on inside this battery. There's some mass balancing, and there's some charge balancing and some other things going on. But I'm just showing you two of the dominant equations that are going on. And if these two dominant equations are solved, then you can come up with a great amount of insight of what's going on inside your battery. And these are based on things like the Faraday constant, universal gas constant. You have to know the electrode potentials of the materials, the materials that you're using. Over here, the porous electrode surface area, the molar volume. And so with some of these really basic fundamental physical chemistry parameterizations of these models, we can model now what is actually happening in our battery of the lithium ion diffusing out of one of the particles and into the other particle. And it gives us a great deal of insight of what's happening inside the battery. So when I take a look at this empirical versus physics-based model map that I began my presentation with, I drew a red line right through the center of it now, because there's no longer a continuum of models. There is an absolute difference between empirical models and physics-based model, and they cannot be viewed as a continuum, because an empirical model is based off of terminal behavior. You have to look at it from the outside of the battery. You measure it at the terminals. You don't really know what's going on inside the battery. It's a great model for estimating the performance of the battery. It has really low parameterization requirements. You can do a couple tests with the battery, you throw it in a thermal chamber, you can cycle the battery, and it's got low CPU requirements to run. But moving over to the physics-based model, it's a completely different paradigm now, because what you're trying to figure out is what's going on inside the battery. And it also predicts the terminal behavior, but it requires a much, much deeper understanding of what's going on inside the battery and a much more complicated parameterization. Because on the empirical model, I just simply measure the voltage at the terminal and I'm happy with it. But my physics-based model, I have to know stuff like, well, go back up here and look at it again. I have to know stuff like porous electrode surface area and molar volume, and there's a number of electrons involved in the electrode reaction. So there's a lot of very, very in-depth, deep understanding parameterization to employ on these models, but you're rewarded for it, because with the reward of that, I can go back up and I can look at my degradation mechanisms, and I can start making conclusions of, am I doing these things? Am I treating the battery the way it needs to be treated? I can't see this stuff from outside the terminal. And so the only way I can see it is by modeling it of what's going on in the inside. So with that, I'd like to give you a homework assignment for those people who are interested in this kind of thing. Analog Devices has this swanky little circuit board. I bought one last week, and I know it's not exactly affordable for the student. I think I paid nearly $300 for the entire setup. So it's not exactly cheap, but the Analog Devices guys are absolutely fantastic to work with. And so if you reach out and find some Analog Devices people, they may be able to help you out. You could also figure out how to get one of these in your laboratory. But this part number AD5940 is actually a EIS on a chip, and I spent the weekend with it, and I couldn't get it to work exactly as good as they show it in the data sheets, but I'm working on it, and I figured that I'm going to get there soon enough. And this little board will allow you to draw these Nyquist plots at home. And here's a nice little photo hooked up to a test cell. You hit the go button on it, and it runs a frequency sweep, and it determines the complex impedance and draws you the half circle. And then it continues to apply lower frequencies and shows you a bit of the Warburg impedance as well. So as a homework assignment for those who want to do it, pick up the phone, call your analog devices people, see how you can get one of these guys, and get yourself familiar with Nyquist plots. So I do want to say that I have positions open for hire. We are hiring in Indianapolis. We're putting up a multi-million dollar battery test laboratory, and it'll be a laboratory that is optimized and dedicated to BMS algorithm development and BMS development. So anybody interested in the audience doing work like this, my email right there, stephen.moore@aptiv.com. Shoot me an email, contact me on LinkedIn, or just simply go talk to Professor MoChA, and he'll forward your information to me. So thank you very much for your attention, and thank you very much for the invitation today.